Okay. So slides are visible to everyone. Hello. The slides are visible to everyone.
Yes, sir.
Okay. So let us wait for 2-3 minutes so that everyone can join and then we can start. Okay. Okay. So just a quick recap of what we have done in the last class. So in the last class, we started looking at the unsteady state conduction. Again, that is one of the uh, difficulty we have keep on adding, isn't it? So we started with a simple case and then eventually we started one by one the difficulties like variable area. Then we started with the heat generation source, and after that we have added the unsteady state conduction, isn't it? So again, going forward above that is looking at the transient heat flow in a semi-infinite solid. This is also we have seen in the last class, but I think there were some questions, so we are doing it again in a detail. So as you can clearly see that this is the case of a semi-infinite solid as shown in the figure, maintained at some initial temperature Ti. So initially the temperature of this slab, which is having an infinite length along the x direction, initially has the temperature of Ti. Now what happens at time t equals to 0, suddenly the temperature at this surface on the left hand side is lowered to a value T naught. And then what we are interested in finding out how the temperature distribution is going to vary across this system. So that is what we are interested in. Okay. So initially the temperature of the slab is Ti, and then once you give a sufficient time, you will see that a typical temperature profile which you are expected to get here in unsteady state is something which I have shown here. You can clearly see in the figure the temperature profile which I have shown by a red, that will be a typical temperature profile which we are going to see in an unsteady state conduction. Remember, in a steady state conduction, you get a linear profile, linear straight line you get. You are expected to get a linear straight line, but here you will get a curved line and which will become a flat to the actual value of temperature Ti, since this is an infinite solid, so it doesn't matter how much time you give, eventually the temperature on the right hand side when x equals to infinity is going to be still Ti. Okay, because it's an infinite solid along the x direction. Okay, so here uh, in this case, the unsteady state conduction case, we start with the equation which is dou square T by dou x square equals to 1 by alpha dou T by dou T. So this is the same expression which we have derived earlier for a rectangular solid case. So this is the same equation. You can clearly see here the final expression which we have obtained was 1 by alpha dou T by dou T, and that is equals to dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square plus psi v by k. So now in a given case, in the present case, what we are assuming that there is a heat conduction taking place only along the x direction. So therefore, the factor corresponding to this dou square T by dou y square and dou square T by dou z square. So conduction along the y and z direction is 0. So that we have eliminated. Also, there is no generation term. So this psi v by k is also eliminated. So finally, what is we are left with is 1 by alpha dou T by dou T equals to dou square T by dou x square. So that is what we started with here, isn't it? So dou square T by dou x square equals to 1 by alpha dou T by dou T. That is the equation we started with, isn't it? Again, the heat flux or the rate of heat transfer Q at x equals to 0 will be given as heat flux multiplied by area. So area is A into heat flux will be minus K dou T by dou x at x equals to 0. So that will give me Q naught, capital Q naught. Capital Q naught is nothing but the rate of heat transfer through the outer surface on the left hand side. So is it clear to everyone so far?
Sir, I have one doubt.
Okay.
Sir, you have drawn the temperature profile through red line.
Yes.
Sir, so here T naught is greater than Ti, right?
Read the sentence which I have written up. The surface temperature is
Okay.
suddenly
Sorry, sir.
lowered.
Yes, sir. I got it. Sorry, I didn't read the question carefully.
Okay. So initially the temperature was Ti, but as we have lowered the temperature Ti at the surface to T naught, a typical temperature profile which we are supposed to get is something which is shown by the red line. Is it correct?
Yes, sir. It's correct.
Okay. So now here on the left hand side, I have directly written the final expression, but we will see the detailed derivation of this equation on the right hand side. Okay. So here you can see the boundary conditions are on the left hand side. You can see the boundary conditions are the temperature at any x and 0 time is Ti. So this temperature of this slab at any x at time equals to 0 is Ti. But then for any time t, if I look at the temperature at the surface here is T naught, isn't it? And in between the temperature will be T, capital T. And the temperature on the right hand side boundary at x equals to infinity is going to be same as Ti for any value of time t, isn't it? So these are the three boundary conditions in this case we are going to have. Okay. So now in order to solve this particular situation, this situation is also similar to, if you remember, your boundary layer type of problems which you have done in your fluid mechanics as well as in transport phenomena. So how we solve the boundary layer problems? In a boundary layer problems, in general, the equation we dimensionalize, non-dimensionalize, isn't it? Why we non-dimensionalize? Because along the width it can be considered as an infinite, because even before that gradient reach to the end, it will never reach to that end, isn't it? So in a way it is infinite. width, isn't it? So same thing is happening here. If you look at this particular slab, so this temperature distribution is not reaching to the end of this boundary, isn't it? This end of the boundary we are not. In fact, if you look at the temperature distribution, maximum temperature distribution is up to this, isn't it? So in a way, even though in a actual real life cases, this width we know, but for this particular problem statement, this width still be considered as a infinite, because this temperature profile is not reaching to the temperature distribution, or this variation is not reaching to the end of the boundary. So that is something called as infinite length here. Okay. Now, in order to solve such problems, we need to find out the width till which we have the distribution of temperature or distribution of velocity in case of boundary layer, isn't it? So that is the reason why whenever we have such situations, generally the length or the width is basically non-dimensionalized, isn't it? So because this x here is infinity, isn't it? So instead of taking this x as a infinity, if we non-dimensionalize and keep the characteristic length till which there is a distribution of the temperature is, then it becomes easy to solve this, isn't it? Okay. So now, in order to solve this particular problem, we start with this final expression, which is dou square t by dou x square, which is equals to 1 by alpha dou t by dou t. So in this equation 1, in order to solve this equation 1, the temperature T is again represented using another variable theta. So theta here is defined as T minus T naught. Okay. So this equation 1 can be represented in the form of theta as dou square theta by dou x square equals to 1 by alpha dou theta by dou t. Here T naught is a constant value, so it doesn't matter. Even if we put theta equals to T minus T naught, we are going to get a similar form as that of equation number 1. Okay. So again, as I said, this x is a infinite width, infinite length here. Definitely we need to have something variable which is finite here, so we can use a characteristic length in order to non-dimensionalize this x. So that can be done using another variable which is nothing but eta. So this eta basically non-dimensionalize this x using a characteristic length, which in this case is under root alpha t. Okay, so this specific form of this eta, in this case we have selected this form of eta in order to simplify, but there is some rationale behind selecting this specific form. So in fact, if you solve this particular problem, particular problem with some fixed length of this width, then you will get this characteristic length as x by under root alpha t, something like that. You will get it if you solve it for a different condition. So there is some knowledge available that what should be the characteristic length here. Okay. In fact, based on that particular thing, we can put this another variable eta, which will be a non-dimensionalized variable instead of x. So this eta is given as x by 2 under root alpha t. So if we put this eta in this equation number 2, equation number 2 is then simplified to another equation, which is equation number 3. So dou square theta by dou n square plus dou square theta by dou eta square plus 2 eta into dou theta by dou eta equals to 0. Again, here the boundary conditions are, some confusion was there with respect to this boundary condition. So let us look at this boundary conditions in a little bit more detail. So let's take time t equals to 0. So at time t equals to 0, remember this temperature is going to be Ti. So theta, which is nothing but T minus T naught, which is going to become Ti minus T naught. So that is represented as theta I. So this first boundary condition is correct, isn't it? Now second boundary condition at x equals to 0. So that is the boundary of this slab here. that is the boundary of the slab. So here at any time this outer temperature is still going to remain T naught. So at this surface, this T is going to be same as T naught. So what theta we are going to get is T naught minus T naught, that will become 0. So at this boundary, at any time T greater than 0, we are going to have theta equals to 0. And the third boundary condition is applied on the right hand side of this slab here at x equals to infinity. So at x equals to infinity, doesn't matter how much time I am giving, ultimately this temperature here at the boundary is still going to remain Ti, and therefore at this boundary at any time T greater than 0, my theta is going to be same as Ti minus T naught, and that is going to be theta I. So all these three boundary conditions are now correct. Is it correct? Are you all able to follow now? Hello?
Yes, sir. The boundary conditions are correct now.
Okay. So now, once we have, we know the boundary conditions, we know the final expression, which is nothing but this equation number 3. Now it is just a matter of, solving this equation number 3. Now equation number 3, the form of the equation number 3 is such that we can obtain the solution of this equation in terms of the integral, which is given as exponential of minus eta square dn. So this integral is obtaining the analytical expression of this integral is not possible. Okay. But we can write down the solution of equation number 3 in terms of this integral, which I have shown here, which is integral exponential of minus eta square dn. So this integral is not, we are not able to solve this integral analytically, but we can write down the solution of equation number 3 in terms of this integral. Okay. So let us apply the boundary conditions here. So as theta tends to theta I, sorry, maybe I just go to the next page, then things will be clear. Okay. Okay. So let us look at this equation number 3. Equation number 3 is dou square theta by dou eta square plus 2 eta into dou theta by dou n, and that is equals to 0. This is equation number 3. Boundary conditions are when theta is tends to theta I, eta tends to infinity, that is the first boundary condition. And when theta equals to 0, eta tends to 0. These are the two boundary conditions. Now let us look at the analytical solution of this equation number 3 in terms of that integral, for which we cannot find out the analytical expression of that integral, but we can write the analytical expression in terms of that integral for this equation number 3. So the solution of equation number 3 can be written as dou theta by dou n will be written as C1 exponential of minus eta square. And again, if you integrate it further, you can write down theta as C2 plus C1 integral exponential of minus eta square d eta. Okay, so this is the final expression which we have obtained. The only difficulty here is solving this integral. Okay. If you look at the actual solution of equation number 3, actual solution of the equation number 3 is ln dou theta by dou n, and that will be equals to constant c minus eta square. So that ln which is on the left hand side, you can convert back, take it back on the right hand side. So that will become exponential of c constant into exponential of minus eta square. So exponential of the constant c is represented as c1. So dou theta by dou n can be represented as c1 exponential of minus eta square. And if you further integrate, what you get is c2 plus c1 integral exponential of minus eta square d eta. Now, this particular equation, since I am repeatedly saying that finding the solution of this exponential term is not easy. Analytical solution of this exponential term is not easy, and therefore this exponential, this integral term is represented in the form of error function. So that is, error function is defined as, error function eta is defined as 2 by under root pi integral 0 to x by 2 under root alpha t e raised to minus eta square d eta, and the values of this error function for different values of this z can be, is already given and is tabulated here. So here you can see, as the value of z varies from 0.00 to 1.3.0, the error function varies from 0 to 1. So values of error function, values of this integral is tabulated. Analytically, it is not possible to get the values, but we know the values numerically, and these are tabulated here. Okay. So these are tabulated here. Okay. So now let us apply these boundary conditions to this final expression here, equation number, maybe let me just number this particular equation as equation 4. So now we can apply the boundary condition to equation number 4. Just wait. Okay. So now the boundary conditions are theta equals to theta I when eta equals to infinity, isn't it? So and another boundary condition is theta equals to 0 when eta equals to 0. So apply the second boundary condition first. So theta equals to 0 and eta equals to 0. If you put it, what you get is C2 equals to 0. So this C2 comes out to be 0. Okay. Then you apply the first boundary condition. So first boundary condition, theta equals to theta I when eta equals to infinity. If you put it in this equation, what you get is C1 comes out to be 2 theta I divided by under root pi. So if you put this C1 in this equation, C1 and C2 in this equation number 4, what you get is theta is equals to theta I error function eta. So here theta is what? Theta is what? T minus T naught, whereas theta I is what? Ti minus T naught, isn't it? So this becomes T minus Ti divided by Ti minus T naught, and that is equals to error function. So that is what I have written here. This is what the final solution, isn't it? T minus T naught divided by Ti minus T naught equals to error function of eta. See, this x by 2 under root alpha t is nothing but eta, isn't it? So this is what the final solution. This equation number, let's say 5. Let me just write down that also. This equation number 5.
So would we have to understand this function, the working of this function, so as to solve questions later, or can we just use the direct results? Because we don't know that how exactly when eta is going to 90, this will turn out to be root pi by 2.
What you are trying to say? Please come again.
So like, do we have to understand this entire algebra of error function as well? Because we don't know that when eta is going to infinity, this error function would give a output of root pi by 2.
So I have already tabulated the values of error function with respect to eta here.
So that is for finite z, no? Like later.
So above this, whatever the value of z, you will have error function z is going to be just 1. That is varies between 0 and 1. This is the ultimate limit. Above this, whatever the value of z you can have, the error function is still going to be the value equals to 1. Error function varies between 0 and 1.
Okay, sir.
You got it?
Yes, sir.
So for any value, if your z value is infinity, still your error function is going to be just 1. Clear?
Yes, sir.
Okay. Okay. So now let us look at how the rate of heat transfer can be obtained from this. So based on this, now we got this final expression, which is nothing but this. T minus T naught equals to divided by Ti minus T naught equals to error function x by 2 under root alpha t. Okay. Okay. Now what we are interested in is to find out the rate of heat transfer. And how we find out the rate of heat transfer? Rate of heat transfer is nothing but what? Area into the heat flux at particular location x, isn't it? The rate of heat transfer is given as the heat flux into the area. So now the heat flux we can directly obtain by differentiating this particular equation, this final equation. We can differentiate this final equation and then multiply it by K and area. So that will give me directly the value of Q, isn't it? So dou T by dou X we can directly obtain by differentiating the expression which we have obtained for the temperature distribution. So by differentiating this equation, what we are getting is Ti minus T naught divided by under root pi alpha t exponential of minus x square 4 alpha t. So this term which is inside the bracket is nothing but what? Eta square, isn't it? This bracket term is nothing but eta square, correct? X by 2 under root alpha t is the eta. So we have just having the square here. Okay. So now the heat flow at any x, can be obtained as this dou T by dou X into minus K into A. That will give me the capital Q. So that is what we have done. We have just multiplied by minus K and A, isn't it? So that will give me the heat flux at any location x. At any location x from the left hand side, isn't it? Again, we can find out what will be the value of Q naught exactly at the surface of the exactly at the surface of the slab. So exactly at the surface of the slab, Q naught will be given as minus Ka Ti minus T naught divided by under root pi alpha t, because x equals to 0. So if we put x equals to 0 in this, this particular factor becomes just 1. So what we get is Ka Ti minus T naught divided by under root pi alpha t. Okay. So one more thing is important to note here. Unlike the steady state conduction which we have seen earlier, in steady state conduction, remember we have assumed that capital Q was remaining constant as we were moving along the x direction, or we were moving along the radial direction, isn't it? Small q or the heat flux was varying, but capital Q used to be constant, isn't it, earlier? That was because there we were looking for the steady state. Here we are looking at the unsteady state, and therefore this Q and this Q naught will not be same. These will be different. So these are the points we have. These are the small minute points which one has to remember here. In unsteady state conduction, capital Q is not constant throughout the width. Okay, is it clear to everyone?
Please repeat
Okay.
once.
So what I'm trying to say is, if we go back, let me just go back. So whenever we have looked at steady state conduction, remember this capital Q, we have always kept it, constant. This capital Q we have assumed to be constant throughout, isn't it? So
Yes,
for
sir.
example, if we apply, let me just go back to the previous case, maybe. Okay. So this Q was remaining constant, remember, isn't it? So this small q, which is nothing but the heat flux, used to vary, but this capital Q used to remain constant. Remember, rate of heat flow is always constant, isn't it, in earlier cases? So that was because we were looking at the steady state heat conduction there. But here, if you look at these cases, here this q which is at any location x, that means basically this q we are looking at somewhere here in between. So q, capital Q here somewhere in between will not be same as the q outside, this q naught here at the boundary. That is what I'm trying to say. In earlier cases, whenever we have looked at the slab, this q is to remain constant throughout the width of the plane. Is it correct to is it clear to everyone? Is it clear to everyone?
So like,
Still not clear?
so the latter part is not clear. Earlier Q was constant, that is clear, but what is the new thing that you want to tell over this case?
What I'm trying to say is the q, capital Q is also going to vary in this case. Earlier case, capital Q used to remain constant, small q used to vary. That's it. But capital Q used to remain constant throughout.
Yes, sir.
In this case, the capital Q will also vary as we move along the x direction. Clear? Because it's an unsteady state. We have not yet achieved the steady state. Clear?
Right.
Okay. Now, another question one can ask here. Now it says, remember it's a semi-infinite solid, isn't it? So the another question can be asked is, if I, keep the temperature of this surface to the temperature equals to T naught, let's say for 5 hours or 6 hours, how much will be the total energy or total heat given as a input to the solid? Okay, that kind of question can be asked, isn't it? So that can be directly obtained. The total heat added over the time interval between 0 to T can be obtained directly by integrating this Q naught with respect to time, isn't it? So that becomes integral 0 to T Q naught dt, isn't it? So we can integrate this equation Q naught with respect to time, and what we get is 2 Ka T naught minus Ti divided by under root pi alpha T. Clear? Pi alpha by T. The one more thing to note down here is when you are calculating the total heat added over the time interval, basically what you are calculating is joule per meters per unit area. If you are calculating, then you are calculating joule per meter square, isn't it? So here make sure that all the quantities you use in SI unit. Okay. So that is one requirement, because this time here this is pi alpha by T, isn't it? So that is not getting cancelled out, isn't it? So you have to use the SI units here throughout. Okay. Okay, the another point which we have seen in the last class was a Biot number. Some confusion was there with respect to the description which is written here at the bottom. So Biot number is defined as HS by K. So that could be HD by K, that could be HL by K, where S is a characteristic dimension which can be diameter, which can be even the length, isn't it? Physical significance of the Biot number is it basically compares the surface convection to the internal conduction resistance. So surface convection is given by this H. So H is nothing but the heat transfer coefficient, which is characteristic of the convective heat transfer, isn't it? Whereas K is small k, which is there in the denominator, is a characteristic of conduction. Okay. So what we have said in the last class is when K is very high, in that case, what will happen? The conduction resistance is negligible compared to the convective resistance. And in such cases, we get a small Biot number. But there was an argument by some students saying that even H can be low. Yes, we agree H can be low. But in most of the cases, you will see H is slightly higher value. But yes, that point is not refuted at all. H can be even smaller value. Okay. Okay. So basically, depending on what the value of denominator and the numerator is, you can only compare whether the in terms of the magnitude, the conduction resistance is significant or the convective resistance is significant. That's it. Okay. So is it clear to everyone? Hello? Can we go ahead?
Yes, sir.
Sir.
Let us look at one simple problem based on the semi-infinite solid, since this topic was little bit confusing to the students. By solving this problem, probably you will have some more light on what we are doing. Uh, the statement of the problem is calculate the temperature in plane which is 200 mm from the surface of a very thick wall, and also the heat flowing per unit area of this plane 10 hours after the surface temperature of the wall changes from 25 degrees Celsius to 700 degrees Celsius and remains constant thereafter. Also find the total energy taken up by the wall in 10 hours per unit area. Assume the thermal conductivity equals to 0.7 watt per meter Kelvin, and the diffusivity is given as thermal diffusivity is given as, so that is K by rho Cp, that is given as 0.003 meter cube per hour. Okay. Sorry, meter square per hour. This is meter square. Okay. So can you solve this problem? I will give the solution, but just try to make the solution of this problem. Let us see. Okay, so what is been given is we have to find out the temperature at the distance 200 mm from the left hand side. Okay, now the expressions, all the expressions which we know here. So these are the expressions, isn't it? This is the first expression, isn't it? This is the first expression. You already know what is the value of alpha. You already know x equals to 200 mm. You already know the time also, isn't it? Correct. Based on that, find out this eta. Then based on the eta, find out the error function of eta using this table, isn't it? Using this table, and then put the value of error function in this equation and find out what will be the temperature, what will be this temperature T at the location of 200 mm after 10 hours. Okay, is it clear? So can you do it? Hello.
Yes, sir, we can do.
So find out the value of error function eta first. So this is the table. This is the table. Find out the value of error function first. So what will be the value of eta? Anybody? What will be the value of eta? Eta is again defined as here. You can see x by 2 under root alpha t. That is what the eta is. X by 2 under root alpha t. So x is already given. X is given as 200 mm. So 200 mm you can convert it in meter, divided by 2 into under root alpha. Alpha is also given 0.003, and the time is also given, that is 10 hours. So you can put 10 hours, find out the value of eta first. Then once you know the value of eta, find out the corresponding value of error function. You will not get exactly at the boundary, so you will have to interpolate between the lower and the upper limit between in which this particular value of eta is getting mapped, isn't it? So just
So
by
we have to. So do we have
yes,
to change the time in seconds, like, or should we keep it in hours?
Doesn't
Like how
matter
is it?
because it doesn't matter because alpha is given in meter square per hour, isn't it? So if you
Okay,
multiply
okay, okay,
that
sir.
by 10 hour, that hour will get cancelled out. So it doesn't matter. Clear?
Yes, sir. I didn't say that. Okay.
Sir, while interpolating, do we have to assume like linear between two limits?
Sir, is eta something around 0.577?
So this is the value of eta. Did you get it?
Yes, sir.
0.577 is the value of eta. Find out the value of error function of 0.577.
It'll
I
be from
can
the
show you
table.
the table. This is the table. Okay. So 577 means 0.5 and 0.6 in between here is the value of eta, and corresponding error function you have to find out by linear interpolation. So that comes around 0.58. Are you all getting around that value? 0.58 will be the value of error function eta.
Yes, sir. 0.5821 something around.
Yes, sir.
So around 0.585 is what the value I got. Now you can put it in that equation and back calculate the value of temperature, isn't it? So that comes around 305.12 degrees Celsius. So are you all getting? So you just have to put the values here, all the values, and you can just back calculate the value of temperature. So that comes around 305.12. Just check whether you all are getting the same value. I might have made some mistake also. So just check the values.
Yes, sir, it is correct.
It is correct. Okay.
Yes,
So
sir.
now based on this, now this is the first part. Now again, what is been asked is what will be the value of Q, rate of heat transfer at the location 200 mm from the surface after 10 hours. So find out the value of Q. Again, you can use the expression which is here. This expression you have to use, isn't it? So by using this expression, you can find out what will be the value of Q, rate of heat transfer at the location X equals to 200 mm. So everything is known in this equation.
So can you please repeat what you were saying?
Find out the value of Q. Find out the value of Q at the location X equals to 200 mm and the time is given as 10 hours. Everything is known. Alpha is known, Ti is known, T naught is known. Isn't it? In this equation, everything, even thermal conductivity is known. You have to find out Q per unit area. So this area is also known. That is 1 meter square. Isn't it?
Yes, sir.
So find out the heat flux per unit area. So what is the value of Q? Anybody got the value? So this is what you are expected to get. Check whether the calculation is correct or not. Just check. I might have made some mistake also. So please check the calculation.
Yes, sir, it's correct.
Okay. Now in the last part, you have to calculate the total energy taken up by the wall in 10 hours per unit area. So you have to find out how much total energy is supplied at the surface in 10 hours. So what you have to calculate is, I can go back, you have to calculate this total heat added over the time interval 0 to t. So calculate this. So this is going to be the expression, isn't it? Calculate the value of total amount of energy. Again here note down, see in earlier expression alpha and t were multiplied, and therefore it doesn't matter even though we have used alpha in meter square per hour, isn't it? Because time was also in hour. But here it's not multiplied. Alpha and t is not multiplied. Both are divided, isn't it? Alpha is divided by t. So therefore you have to use alpha as well as this t both in seconds, isn't it? Clear? Otherwise you will end
Yes,
up
sir.
with getting a wrong answer.
Yes, sir.
So why would we get the wrong answer? Because like we will get the answer in hours only.
Because you will get the answer in joule, isn't it? Joule per.
Okay, okay, yes, sir.
So there, see, joule is not defined in terms of R.
Yes, sir. Got it.
Sir, what is capital A over here? The area. So would we assume it to be square or what?
That is
It's
why
given unit
it
area
asks per
one.
unit area, isn't it? So that means this will go on the left hand side here, isn't it? So you can use assume equals to 1 per
Okay, okay.
unit area. You will get it,
Yes, sir.
isn't it?
Yes, sir. Yes, sir. Yes.
So what we are expected to get is this answer. Just check whether you all are getting the same or not. 1.108 into 10 raised to the power 8 joule per meter square. So remember here in the denominator you will get 3600 square. So that will go in the numerator as 3600.
Sir, won't it be root 3600?
What you are saying?
So root 3600 because it's
Square
root.
will be there because both time as well as alpha both are given in per unit in hour, isn't it?
Ah,
So
yes.
alpha is given meter square per hour. So that also you have to convert it into meter square per second, isn't it?
Yes, sir, yes, sir.
So that will be 3600 square. So that will go in the numerator then. Is it correct?
Yes, sir.
Can we move to the next? Is it clear to everyone? Okay, so I think let us move to the next topic. So again, see, this is the last topic of this conduction chapter, and so far we are, keep on adding, difficulties one after another. So let us look at one more, difficulty. Let us add in our analysis. So far we were only looking at, one-dimensional conduction, isn't it? One-dimensional conduction we have looked at. What is the analytical expression, even though we have looked at, three-dimensional conduction also, but we have not obtained the analytical expression, isn't it? If I go back, these are the, three-dimensional, this is two-dimensional, but here we have not obtained the analytical expression, we have not solved it, we only obtained the final energy balance equation and we have stopped there, isn't it? So let us look at the analytical solution of two-dimensional flow conduction through a slab, and this is the last chapter. Okay, this is the last topic in this particular chapter. Okay, so in many practical situations the real heat conduction takes place along more than one dimension. This is especially true if the system has irregular boundaries and with non-uniform temperature along boundaries. The temperature in these systems may vary in 2 or 3 coordinate directions, and multi-dimension heat conduction analysis must be made in order to understand temperature distribution or heat flow through these systems. The commonly used examples are the heat treatment of metallic parts of different shapes, composite bodies, chimneys, air conditioning ducts, etc. So let us look at the mathematical analysis of 2D system. So consider a plain rectangular plate as shown here. The temperature at any section Z is constant, and we are only looking at the temperature distribution along X and Y coordinate. So temperature is just a function of X and Y. The general equation for the temperature distribution in 2 dimensions for steady state conduction is given by dou square T by dou X square plus dou square T by dou Y square equals to 0. So this is the typical Laplace equation. I can go back and show you again. So this is what we are trying to solve. Laplace equation. Remember, we are not using any generation term, we are not using any accumulation term. So what we are going to get is del square T equals to 0. So in a 2 dimension, what will be del square T? That will be only dou square T by dou X square plus dou square T by dou Y square equals to 0. That is what we are expected to get for a simplified case. So this is what the system is. On the left hand side, the temperature on the slab surface is 0. On the right hand side, when the width is equals to along the X direction, when the width is equals to A, the temperature is again 0. Along the Y direction, when Y equals to 0, the temperature is given as a function f of x. So this function t equals to f of x could be a constant value. It could be any variation, because this could be connected to some other wall. So you might have a sinusoidal type of temperature profile as well here. Okay, so this t equals to f of x is any function which could be a constant value, or it could be a sinusoidal function as well. Both options are selected here, and when y equals to b, so this width along the y direction is b, then the temperature is also equals to 0. So on 3 boundaries the temperature is 0, and only at the bottom the temperature is equals to f of x, where f of x is any function which could be a constant value, which could be a sinusoidal function also. Again here these lines which I have shown, these are the constant temperature lines. So this, see, there are 2 types of lines. One type of lines which I have shown is the energy lines, and below these energy lines, these are the horizontal type of curved lines are there, isn't it? So these are nothing but the isotherms. These are nothing but the lines with the constant temperature, and the energy lines are always perpendicular to the isotherms. That means the heat is transferring in a perpendicular direction to that of the isotherms. Is it clear to everyone? So heat will be transferred along the perpendicular direction of the isotherm. Clear? So now this equation number 1, which is a Laplace equation, we wanted to find out the analytical solution of this. Of course, the numerically you can solve all this CFD and all is, they able to solve even much more complex heat transfer problems. But here, just for the sake of understanding, we are solving a very simple problem of Laplace equation, two-dimensional Laplace equation analytically. Okay. Is it clear to everyone what we are saying? Hello? Can we go ahead?
Yes,
Am I
sir.
audible? Okay. Yeah. Okay. So now, what are the boundary conditions? Boundary conditions are at x equals to 0. At x equals to 0 along this end, the temperature is 0. At x equals to a, again temperature is 0. At y equals to b, that is this end, t equals temperature equals to 0. And at y equals to 0, that is at the bottom, t is given as any function f of x. So these are the 4 boundary conditions. Now, in order to solve the Laplace equation, which I have given earlier, the equation number 1. So variable separation method is used. Variable separation method in which there are 2 different variables, capital X and capital Y are used, isn't it? And the solution of this equation 1 is represented as capital X, X and y, where small x and small y are the independent variables. And xx is a function of x alone and yy is a function of y alone. Okay, so this is what is been given. So this is the solution is assumed. Solution 2 is assumed. Okay. In a variable separation method, 2 separate variables are assumed, and based on that the solution is also assumed. And now we are trying to check whether this particular solution is correct or not. So this solution is correct only if it satisfies all the boundary conditions, isn't it? That is what we have to do in this case. So now, based on equation number 2, equation number 1 can be further simplified as if we put equation number 2 in 1, what we get is 1 by capital X d square x divided by dou x square, and that is equals to minus 1 by y dou square y by dou y square. And since now this y and x are independent, this partial derivatives we have removed. So now we have got the second order ordinary differential equations. Okay. So this equation number 3, again you can see the left hand side is independent of the right hand side because x and y are independent of each other. So that means both these can be solved separately by assuming some constant equals to some constant. Okay. So some discussion before we go for solving this. Since each side of this equation number 3 is independent of the other, x and y being independent variable, it follows that each side may be equal to a constant. Okay. Again, in order to find a proper solution of 3, it is essential to select a proper value of this constant. So this left hand side should be equals to a constant. At the same time, this right hand side should be equals to the constant because both these left hand side and right hand side, these are independent of each other, and the proper value of this constant has to be selected. So now we can select, let's say, a constant equals to 0. So 1 by x into dou square x by dx square equals to d square x by dx square equals to 0. So that is the constant value. And similarly 1 by y d square y by dy square equals to 0. If we select a solution in this particular form, what we are going to get is we are going to get a linear solution, isn't it? So we are going to get x equals to c1 plus c2 x, something like that. A linear solution is going to be there for both x and y. So in such cases, if we apply the boundary conditions are not satisfied. So clearly the constant cannot be 0. That one option is eliminated. Now second option, let's look at the second option. let us select a positive constant. If we select a positive constant, so 1 by x equal into dou square x divided by dx square equals to, let's say, lambda square. Lambda is another constant, let's say. So if we use even a positive constant, in that case also the boundary conditions are not satisfied. I have not derived those cases here, but you can extensively see those derivation in the book. I am only giving the discussion on that. Okay. So if you select even a positive constant, in that case also the boundary conditions are not satisfied. Now the last option remaining is the negative value. So if we select a constant, something 1 by x dou square x divided by d square x divided by dx square equals to minus lambda square. If we select this particular form, then the boundary conditions are satisfied for both the cases. So clearly we have to select this constant here as minus lambda square. So in this case, if we put 1 by x d square x divided by dx square equals to minus lambda square, that minus lambda square can be taken out on the left hand side. So what we are going to get is d square x divided by dx square plus lambda square x equals to 0. Similarly, the same constant has to be there for the another factor which is on the right hand side. So minus 1 by y d square y divided by dy square equals to minus lambda square will be there. So that minus sign we can get rid of, and if we move this right hand side to the left hand side, what we are going to get is d square y by dy square minus lambda square y equals to 0. So these are the two equations which we are going to get from equation number 3 based on the boundary conditions which are present in the problem. Okay. Now let us obtain this. Now it is easy to solve equation number 4, because equation number 4 is a standard form of double differential equation for which the analytical solution we already know. So this is equation number 4. The analytical solution for each of these differential equation we can write down here directly. This is already known analytically. So x is obtained as a sine lambda x plus b cos lambda x. Similarly, y can be obtained as c sine hyperbolic lambda y plus d cos lambda y. Remember why lambda square is selected, that you can now visualize here, because you are getting a lambda term here. Otherwise, if you would have selected only a lambda term, you would have got under root lambda here. So that is why a specific choice of lambda square is used here. Okay. Now remember, what is the t? T is nothing but x multiplied by y. That is what we have assumed initially. Remember, t is nothing but x into y. So x into y, that is going to give me t. Now I just have to put the boundary conditions and find out the expression for the t. Okay. Now let us look at the first boundary condition. What is the first boundary condition? When x equals to 0, t equals to 0. That is the first boundary condition. If we put it in this equation number 6, so what we are going to get, again remember, when we are putting this first boundary condition, y is equals to 0. So this factor becomes just 1. So in this case, if we put the boundary conditions, what we get is the b equals to 0 and a sine lambda a equals to 0, and here in this particular equation a cannot be 0. So therefore sine lambda a should be 0, and that is possible only if lambda is equals to n pi by a. Again, if we put this n pi by a in this equation, what we get is a sine n pi x by a, c sine hyperbolic n pi y by a plus d cos h n pi y by a. Here we can put again the third boundary condition, which is y equals to b at t equals to 0. If we put this, okay, one more thing is there. Remember here, this particular equation here, you are going to get lambda equals to n pi by a, where this n can vary as 1, 2, 3, isn't it? So here basically the numbers n are known as eigenvalues and each corresponding to a Tn, isn't it? So corresponding to each of these n value, the solution obtained will be a Tn, isn't it? Actual solution will be the summation of the entire Tn over 1 to infinity, isn't it? So this Tn, which is the specific solution corresponding to a individual n, is given here. Now apply the third boundary condition, which is y equals to b, t equals to 0. If you put it here, what we get is sine n pi x by a, ac sine hyperbolic n pi y by a plus ad cos h n pi y by a. Now here ac, a is multiplied here inside this bracket. So ac is represented by e and ad is represented by f. Now by rearranging since this sine n pi x by a cannot be 0, only this bracket can be 0, we can rearrange this equation and find out the expression for e. So e can be obtained as, remember this is f, so f cos hyperbolic n pi y, so that is at the condition y equals to b, so that becomes f cos hyperbolic n pi b by a divided by sine hyperbolic n pi b by a, and the negative sign will be there. So this e can be put it in this equation, and again simplified. So that is what is been done here. So by putting the e in this equation, the f now we can take it out as a common. F we have taken it out as a common, so that becomes f sine n pi x by a in the bracket minus cos hyperbolic n pi b by a divided by sine hyperbolic n pi b by a into sine hyperbolic n pi y by a. Remember this is the value of e, isn't it? So this f is there here outside, so that f is also taken out from the bracket. Again here the last term is going to be f cos h n pi y by a, so that f is also taken common from both these factors here, so that is taken out from the bracket here. So again this entire equation, if you multiply, if you take this n sine hyperbolic n pi b by a outside, again this is a constant value, isn't it? You can take it out here. So Tn is f sine n pi x by a divided by sine hyperbolic n pi b by a, and this minus sign will be as it is here, so that becomes cos hyperbolic n pi b by a sine hyperbolic n pi y by a. Remember this is taken out, so this will be multiplied here in the second factor, so that becomes cos hyperbolic n pi y by a into sine hyperbolic n pi b by a, and this entire bracket can be represented in a sine term as sine hyperbolic n pi by a in the bracket b minus y. So this entire analysis simplifies my equation Tn corresponding to a particular eigen value n is given as Tn, that is given as f sine n pi x by a sine hyperbolic n pi b by a into sine hyperbolic n pi a in the bracket b minus y. Okay. Now again here in this case all the constant terms in this equation Tn, in this equation all the constant terms can be represented using Kn. So let us put f is constant. Again sine hyperbolic n pi b by a, this is a constant, so f by sine hyperbolic n pi b by a, that is represented as Kn. So this Tn is represented as Kn sine n pi x by a into sine hyperbolic n pi a in the bracket b minus y. Okay. Remember I said that this particular Tn is corresponding to one eigenvalue, and there are infinite eigenvalues starting from 1 to infinity. So that means the temperature distribution will be obtained as the summation from 1 to infinity, and that is what is been done here in the bottom equation. So temperature T is given as the summation from 1 to infinity, where n is varying from 1 to infinity, Kn sine n pi x by a into sine hyperbolic n pi a in the bracket b minus y and the bracket close. So this is what we have obtained. after doing all the mathematical analysis. Now one more boundary condition we are left to apply. Remember, we have applied boundary condition 1, 2, and we have applied the boundary condition number 3. We have the last boundary condition, which is this boundary condition we have not applied. At y equals to 0, t equals to fx. So let's apply the last boundary condition to simplify this equation further. Okay. So Tn is obtained as this. Now the last boundary condition is what? At y equals to 0, t equals to fx. If I put it fx here and y equals to 0, so what we get? Kn sine n pi x by a sine hyperbolic n pi b by a. So this y is becoming 0 here. So if we apply the last boundary condition, the expression obtained is this. Now if you look at this expression, this equation is similar to what we see in the Fourier transform, isn't it? Fourier series. This is the expression of Fourier series, isn't it? And if you remember your Fourier series, the constant Kn can be obtained in the Fourier series directly by this expression. So constant, remember here the constant is Kn sine n pi b by a. This is sine hyperbolic n pi b by a. This is the constant term. So this constant term can be obtained by a Fourier series analysis as 2 by a integral 0 to a f of x sine n pi x by a into dx. So this constant which we have obtained by a Fourier series, we can put it in this equation back, and the final expression obtained is txy is equals to 2 by a summation 1 to infinity 1 upon sine hyperbolic n pi b by a in the integral 0 to a fx sine n pi x by a dx, the bracket close. This first bracket is corresponding to a constant. So 2 by a in the 2 by a into this entire bracket is nothing but the constant which we have obtained from the Fourier series, isn't it? Multiplied by sine n pi x a sine hyperbolic n pi a in the bracket b minus y. So this is the final expression which we have obtained for the temperature distribution when we are having 3 sides having the temperature equals to 0 and one side is having temperature equals to a function f of x. Now here this is a very simple case we have analyzed. A simple case in the sense we have assumed that all 3 boundaries are having a 0 temperature and only this boundary is having a f of x temperature, isn't it? But let us say we are having a different function at all these boundaries. Let's say the temperature here is also, let's say f1x, here it is f2x, f3x and f4x. So how to calculate the temperature distribution in such cases? In such cases, you obtain the temperature distribution for individual cases and then you add up. That will give you the temperature distribution when instead of 0, you are having some finite temperature function is there, t equals to fx. So that is what we are going to look at here. So this is the case. Instead of looking at a simple case which we have seen earlier where 3 sides are having a 0 temperature, let us assume that all 4 sides are having different temperature functions like f1y, f2x, f3y and f4x, which is a function of y as well as x alone. And in such cases, we can solve this problem by assuming the 0 temperature in the remaining 3 walls and only the temperature function at one wall at a time, and then we can add all the temperature profiles to get a final temperature profile in such cases. So in such cases, the temperature profile Txy can be obtained as T1xy plus T2xy, T3xy plus T4xy. Okay. So this is all about the 2-dimensional heat conduction, and we stop here unless you have any doubt, any question to ask. So this is all about the heat conduction. We will start with the next chapter, that is heat transfer coefficient, in the next class. So is it clear to everyone? Can we stop here or you have any doubt, anything you wanted to ask?
Sir, this what we have studied in the 2D transfer. Do we need to solve problems on this, or just we have to get the qualitative idea of this?
See, I don't know. Maybe see, even if there is a problem, that will be definitely doable. It will not be undoable, isn't it? So whatever we have done in the class based on that, or some extension of that, could be there as a problem if I, give it. Otherwise, uh, I mean, at this point, I don't know whether we can, have a problem on this or not in exams or something. But there are different problems solved in the book on this. You can see the book. Okay, this chapter number 10 in the book. Is it clear?
Yes, sir.
So, but this algebra is kind of new for us because we haven't done much of this earlier.
So that is why entire derivation is given in front of you, isn't it? There is nothing, whatever the information is required, that I have already given in the slide.
Right, sir. We'll try learning more of it.
So in fact, even if I have taken something from some other book, I have definitely given it in the slides. Okay. Even if you don't able to, if you are not able to find out in the book the specific things, please go through the slide. You will get it. It's not that I have, gone through the book only from the one book. I have gone through several books, and then some material from some other books are also added, but clearly keeping in the mind the flow which is there in uh, the actual textbook which we are using. Okay. So the terminologies and other things, I have made it consistent in order to, make it consistent for the students to go through. Clear?
Sir, the Fourier transformation is definitely new to us.
Fourier transform you all might have done in your engineering mathematics, isn't it? So
Sir,
this is the standard Fourier transform. The solution is also directly given. Just for your information, look at B.S. Grewal Fourier transform. There in the first page itself, the solution is given. Clear? Is it clear? It's a standard
yes.
solution for the Fourier transform. I have also not derived that. I have also directly used the final expression of the Fourier transform.
Sir, which book you said?
Engineering Mathematics by B.S. Grewal. You can look at the even Erwin Krasing. You can look at no problem. There also you will find the solution. So maybe I just go back. Let me just go back. Okay. So this is what you are saying, isn't it? This is a standard solution. This final
Your
expression.
screen is not visible. You have turned this share screen.
Just wait. Let me just open. This expression is a standard solution. I have not derived. I have directly used it. I have directly used because this summation is a similar to Fourier series. This summation is similar to the Fourier series, and therefore the solution is also given in terms of a Fourier series directly. So this constant kn into sine hyperbolic n pi b by a, that can be directly represented as a solution of Fourier series 2 by a integral 0 to a fx sine n pi x by a into dx. Clear? Can we stop
Like,
here?
are these inverse function or something of that sort? Like, because the second expression is using.
So if you look at the Fourier series, there you will see the constant a naught, an, and bn. So an are the constants corresponding to the sine series, bn are the constants corresponding to the cosine series, and a naught are the constants, isn't it, algebraic thing? So there you can see the solution of a naught, an, and bn. All three are given in terms of the sine functions in a Fourier series. That is a standard solution of the Fourier series. Clear? It's just the first page of the Krasig or even the B.S. Grewal book. It's nothing new. In fact, you can look at in the Google also, you will get the same thing. Okay? It's not new. you have not done the Fourier series so far? Just the question.
No, sir.
Okay, so that is why this question. I'm really sorry. So then you can just consider this as this is a standard solution. Okay, and you just have to solve. You just have to solve this integral. That's it. Okay. I thought that you have done the Fourier series, because in our case in engineering mathematics we have done Fourier series, Fourier transform, etc. But in your case, since you are saying you have not done, please look at Fourier series in little bit more detail. This is the standard solution of the Fourier series. Okay. Clear? I'm sorry. I thought that you have already done.
Sir, I had one doubt that in the second expression, we have kn expressed in terms of fx, whereas in the third we have fx expressed in terms of kn. Like, so how are both of these related?
Which one? This one and
In the
this.
second expression, kn is on the right hand side while fx is being expanded, whereas in the third expression, when kn is being expressed, so that is in
The
terms of an integral of fx.
point is fx is known. Fx is known. Kn is unknown.
How is fx known when kn is used to determine fx?
Remember what is been given here? This boundary condition is given to us. Fx is known to us.
Okay, so kn has been derived out of that.
Yes, kn is calculated based on that. Yes.
Okay, sir.
That is why this fourth boundary condition is applied. Fourth boundary condition is applied in order to determine kn.
Okay, sir. Got it.
So kn as well as this see, in this case the kn is unknown, but this other factor sine hyperbolic n pi b by a, this is also a constant factor, so this is also clubbed along with kn. That's it.
And finally, we have substituted kn in the top expression to obtain the function for t.
Then this entire thing we have substituted in the top expression in order to obtain the temperature profile. That's it.
Okay, sir. Got it. Yes, sir.
Okay.
Yes, sir.
So I am sorry, this last topic is little bit complex, but please go through. Other than that, everything I think you have fairly understood, probably, isn't it?
Yes, sir.
Okay, so we stop here unless there is some more questions. So if no question, I am stopping the recording and see you on Monday then.